Thanks for taking the time to learn a little bit more about SOLIDWORKS Simulation. We are going to talk about what I think is probably a drastically underutilized aspect of SOLIDWORKS Simulation. And it really comes into what we call drop test and impact analysis. Two types of analysis that if you're making a product are incredibly important here. So we can go ahead and get started. So, product quality and durability. What does it really matter? What's the big deal? Why do people care about making rugged, robust products that are going to last a while? Well, it's really to avoid this potentially, right? So these are obviously examples of electronics. Maybe they went through a drop test. Maybe this is intended for some of these products, but that's a completely different story. But in general, you want products that are going to be able to withstand anything sort of up to neglect, right? Any kind of neglect, you're not designing to that. Somebody could always misuse your product, but at the same time, there's clearly value in designing a rugged, not an over-engineered product, but an appropriately engineered product that's going to have a suitable lifetime. All right, so the cost of product failures, right? Especially now where things can just go viral. I mean, every day it seems like an airline or a consumer product company is being blasted on Twitter, and there's tens of thousands of people that are seeing that particular tweet, publicizing one of these companies' failures, either in design or service and so forth. So there's a big reputation and publicity hit that can be felt if you sacrifice some of the quality and durability of the product. There's also recalls, right? If things are breaking all of the time in normal use, there's a recall aspect of that, very, very costly. Hopefully we never end up on this third point of actually fines, because some of our product failures actually result in safety hazards, but that can obviously be very expensive. And then there's the ongoing cost as well for support and warranty. That's going to increase orders of magnitude if you don't build quality and durability into your products from the start. So the question is really, can we do this? Can we build durability into the products? This is really what's in it for you all, right? This is why you're here. And the good news is the answer is absolutely. These aspects can be designed into your products from a very early stage of the process. And we think SOLIDWORKS Simulation is one of the areas where we can help out with that. So there's two different types of studies that are going to prove useful in this particular area. One is called a drop test. A drop test is effectively where the object that's being tested is falling, right? Think of it as falling. Now we also have something called an impact test, but you'll never see that as a type of study. Okay, an impact study is really about how we define the study, and typically the object may be fixed and we're going to have some other object with a velocity or a displacement or an acceleration imparted onto it impact the object that we're testing. Now sometimes we can actually move the object as well in a case that I'm going to show you. But the goal is to early in the design process to be able to identify key structural failures that could be introduced that could ultimately affect the quality and the durability of your product. Of course, the earlier that we're able to identify one of those problems, significantly lowers the cost in order to fix that particular problem. So, like I mentioned earlier, the support and warranty and recall costs are significant compared to a redesign effort very early in the conceptual phase where we've still virtualized, we haven't made molds, we haven't made products. It's very easy to make a change when we're still virtualizing our design and virtually testing it as well. So let's dig into these two types of studies. This is one of the main differences. Real quick so that nobody's confused. drop test is a type of study that's included within Simulation Professional. Okay? Impact study, you can do the basics of what I'm going to show you in an impact study with just regular simulation, the same simulation that's included in SOLIDWORKS Premium. The problem is impact is such a violent phenomenon in most cases that if you're solving an impact study as a static analysis, if you're using that linear static assumption, you're probably missing out on the full story of what's happening at the point of impact, right? Drop test and impact are both phenomena that tend to happen in the order of milliseconds. Sometimes microns is where you're really interested in the impacts. A static linear study will not be able to give you that level of detail in your particular study. So really, if you're thinking about, well, what version of simulation is the best one to have if I want to do these types of studies? For a drop test, it's going to be SOLIDWORKS Simulation Professional, and for an impact, it's probably going to be Simulation Premium because you're looking into the nonlinear capabilities at that point. All right, so let's go ahead. Let's dig into drop test a little bit. And I always like giving folks an idea of how you set this up. So there's a couple things with a drop test. There's a couple things to keep in mind. You can set this up as either dropping from a particular height, and then you're just simply setting gravity, or you can set in velocity at impact as well. If you know this thing is hitting, the ground at, X amount of feet per second, then you can go ahead and directly input a velocity as well. You can control how high something is being dropped from. That's where this height field is coming from. With gravity, you can set, of course, the value. It's going to default to just environmental acceleration due to gravity. But more importantly is you can set a direction. Okay, and typically the way we do that is using reference geometry planes in order to define that. All right. We can also set a target. Okay, this is what are we impacting. So this is what would be placed, in our case, 2 meters away from our initial point. So you're going to have some target that the object is going to come in contact with. Now, a lot of times we want the target to be oriented normal to gravity, right? Think of the floor, but sometimes things could be falling onto a slope, falling onto something that actually have some pitch of their own. So you may actually want to adjust that and use a reference plane for that in addition to the one that you specified for gravity here. You can also, here in the middle, under the target area, you can specify a friction coefficient. Now, what this means is when it hits the friction at your object, there's basically going to be a slight sliding impact unless you're dropping something straight down, directly normal and in absolutely the right direction. There's going, and even if you are dropping it straight down, there's still going to be some friction that's going to interact between, let's call it your floor or your target, and the object itself. So we can build in a friction coefficient into that as well. One of the last options that we can set is our target stiffness. In most cases, we're going to assume a rigid target. So our rigid target is going to assume that whatever it's hitting is infinitely strong. Okay. Imagine the thickest piece of the hardest material that you can imagine. There's going to be no give in the target itself. With flexible target, of course, we can go ahead and build in a strength value that's something clearly less than infinite strength, and we can go in and analyze that. In that situation, the assumption is that the target is probably absorbing some of that energy, so the actual model is going to experience a little bit less stress as it impacts the target. Moving down, the very last thing you have here is damping. So you can build a damping ratio. If you're wondering what damping is, drop a bouncy ball on the floor. what you see at that point, that's damping, right? So you would see dissipation of that. You would absolutely see some dissipation of that energy on each subsequent bounce. But every object is going to have some amount of that cyclic bouncing, right? There's going to be a rebound, and then there's going to be a usually much smaller secondary hit as well, but you can control that by putting in a damping factor. Now, typically, you're going to want to, in order to get that damping factor, you're probably going to have to go through some experimental data in order to be able to accurately determine that. Typically, it's the first hit that probably severely impacts most of the products, particularly something that is that's metal. Right, it's typically going to be the first impact that's going to make the biggest impact there. The other part, there is a time component to the drop test analysis, where we're interested in what happens immediately at the point of impact and thereafter. So what we're interested in, you can set a time after impact to select when it's going to start recording results. And then from that point forward, you can say how long is it going to, how long is it actually going. So this is basically how long is it going to solve for. This is our start point. This is how many plots is it actually going to create. So in this case, overall time of 50 microseconds, 25 plots. Each plot is going to represent a time step of 2 microseconds. And then what we have down here below is how many data points per plot. So in this case, we have 20 data points. Remember, each plot is going to represent 2 microseconds. So effectively, we're going to have a data point for every 0.1 microsecond, right? So every 10 nanoseconds, we're going to have data that basically stipulates, every 100 nanoseconds, we're going to have data that stipulates what the stresses are and so forth within this particular drop test. Now, there's a couple things we didn't talk about. There's a couple assumptions that are worth talking about at this point. What about air resistance, right? How do we actually model, how our product is going to adjust to air resistance and how is it going to turn and rotate as it falls? It's absolutely something you need to take into account. There's no factor to put that in. So what we typically recommend that folks do is to orient your part a few different ways and then run the same exact study. Right? That way you can determine 5 or 6 different ways that this thing could fall and the orientations that it could ultimately hit the target, and then basically you design off of the most severe. Okay? We always want to take the most conservative, the most conservative approach, which in our case would be the highest stresses based on orientation. Now, what about advanced materials, right? What if you're actually doing this with a plastic material or something that maybe is elasto-plastic in nature? How does that actually function? Well, we'll go through an example dealing with advanced materials. And then let's also talk about what if your floor is something less than rigid? Okay, we'll go through we'll go through an example dealing with that as well. So let me pop SolidWorks up here, and I have a pretty standard pretty standard consumer product, electronic product in this case. It's a digital camera, and maybe what we're hearing, this is maybe our first generation camera, or maybe this is our second generation. But in our first generation camera, what we would hear a lot is that the zoom here would break off quite a bit at various, when this thing was dropped, it wasn't necessarily that our case would be dented that much, but this part would potentially snap off. So that would be the nature of our failure. So we're wising up to the concept that we actually want to go in and say, okay, what if we can virtually test that, right? Maybe we used to not have this fillet here, so what we're interested in determining now is will that fillet spread out the stress evenly enough so that we're not actually going to lead to failure if this camera happens to be dropped here. So let's go ahead and we will simply make a we will make a study at this point. So I'm going to make a brand new study. It's going to be a drop test study, and let's just call this Freefall 01. Okay, because we could potentially run a couple different versions of this. I have some other studies, and I'm just going to make my life a little bit easier. I'm going to copy things like materials. Okay, I'm going to copy those. Maybe my mesh I'm also going to copy just to save a little bit of time for you all. Once we have materials applied, once we have our mesh applied, now your global contacts, this is also extremely important. We are assuming that everything is bonded here, when in actuality you can design a camera like this so that these two parts may actually they may actually fly apart, and some of that energy will be dissipated through kinetic energy. We're not making that assumption here in this case. We're assuming that they are securely fastened to each other, and this is basically, think of this as a single, think of it as a single piece of geometry. It's one unit, this camera. But what we do at this point is we go in and we define our setup. So this is how high are we dropping this from? Are we specifying a velocity instead? We're going to do a height, and we're going to do from the centroid of the we're going to do from the centroid of the model. Now we're going to specify a direction of gravity. In our case, it's going to be horizontal. Now notice the location of this plane doesn't matter, okay? Because we're already assuming 2 meters. Okay, so the fact that this horizontal plane is actually coinciding with our piece of geometry, that doesn't matter. That doesn't impact our study at all. It's still going to factor in the drop height of 2 meters. This is simply specifying a direction. Okay, and if you ever wanted to reverse the direction, you could easily go ahead and do that as well. Right? That's really just going to change how your results look, where it's going to impact, and so forth. So moving down, we're going to keep this really simple. So we're going to drop normal to gravity. We're going to go ahead and we're not going to include friction coefficient, completely rigid target. If you put in flexible target, this is where you can actually build in stiffness values, right? Stiffness values for that particular target. We're pretty happy with how that looks, so we'll just go ahead and hit OK. This is identical interface to the other study types that we have as well. When you start to see green checks, that means that we've met all of those various requirements, and we don't have to define anything there necessarily. We do have to define result options. So if we go in and edit these as well, again, this is going to be how long is our solution time going to be calculated for. This is going to be when do we start saving results. Typically, you're going to want to do that at 0, right? That 0 means right at impact. We're going to want to go through and do that. Once again, this is the number of plots throughout that particular range. Here you can build in something called a sensor, and then you can monitor that sensor with a certain number of graph steps per time step, basically. Once that's all met, we hit OK. We get another green check, and we can go ahead and run this particular study. Now, just because there is a lot going on here, you'll notice this is almost always going to happen within your analysis. It's going to tell you there's unbalanced energy, but that's okay. We're dropping the thing. So the solver is immediately, the default solver is immediately trying to figure out, I need a stable solution, so it's looking for convergence. And as soon as you start a free fall study, that's the definition of divergence, right? You're not approaching any particular solution. It's actually running in the other direction up until the point of impact. So we hit OK. It's going to run through. And what I would say about solution times, expect this to take significantly longer than, say, a static analysis of the same geometry. I want to say this particular example is going to take 2 to 3 minutes in order to run. But don't worry, I'm not going to ask you guys to sit here for those 2 or 3 minutes. Instead, let's hop back into our PowerPoint. And we're actually going to address these last 2 questions at this point. All right. Now, well, here are the results. If we were dropping the camera and we were assuming it was a rigid floor, we're actually seeing significant levels of stress, and they're actually on the backside of the camera there. Keep in mind, our units, these are pascals. All right. So 10 to the 6th is megapascals. So if we're looking at this value, that's almost 1,500 megapascals at the highest point of stress, and that's at the point at which it makes contact there. So that's significant. If this is made out of metal, you have no chance of it not yielding at that point. But remember, this is the most conservative estimate that we could possibly have for this example because we're assuming an infinitely rigid floor. So the floor isn't absorbing any of the energy that's created as a result of the impact. Let's look at a couple other examples, and then we'll go back into the software in order to actually view our results from inside of there, because just seeing the picture here doesn't necessarily tell the whole story. I ran an additional analysis that incorporates a softer floor, and it's not terribly soft. This is basically assuming I believe an 8-centimeter slab of concrete, right? So not soft by any means, but softer than the infinite strength that we had for our target before. What you'll notice is we're down into about the 340 megapascal range. That's probably survivable for depending on what type of materials. If that's aluminum, probably not. But if that's a higher end steel, probably not going to be a problem to be in that particular range. Lastly, maybe one of the things that tells me is I need to be a little bit more particular about material selection. The last study that I had run is actually with an elasto-plastic material. Now the real benefit here is that the material itself, the geometry itself, will actually be able to disperse a lot of that energy due to the molecular structure of that particular material. Right? That's the real benefit of using these elasto-plastic materials, is there's going to be a little bit more give. So if we compare, say, this example with the rigid floor and a completely elastic material or a completely plastic material versus something that's more in the elasto-plastic range, you'll notice the stress is much more evenly distributed, but you'll also notice that our values are far lower. Okay, 158 megapascals, that's probably reasonable. Keeping in mind that dropping an electronic product like this, that's not an everyday thing, right? That's a one-time. If you survive it once, you're probably doing pretty good from a product durability perspective. All right, before we jump up to impact, let's go ahead and let's hop into our study. It looks like we're still working on the study. I could go ahead and cancel that just because I want to show you guys some other result processing functions that we can go through. So I'm going to go through some of these other studies which I had run previously. This is the one with the softer floor. I can confirm that by just editing my setup. And you'll notice I have some, sorry, I think I grossly overestimated the thickness. I think I changed this so it had a much lower thickness for this particular material. But when we look at our stresses, You'll notice they're in line with what we found. But the most important, I think the most useful way to look at a drop test result is probably to animate the result. Okay? So if you come in, it's going to calculate that, and then based on your time step, if you wanted, you could obviously slow these down significantly so that you could actually see time step to time step. So if you look up top here, we're actually counting down the individual time steps, and the microseconds are increasing up to 50. So you'll be able to actually see that. You can also leverage those different time steps when you're looking at the plot itself. You can edit the definition and take a look at whichever plot step you want to, or you can plot across all steps. Okay, but here, as you go through various time steps, it's basically adjusting the time scale at which point you're seeing that particular solution. You can obviously save these animations out as AVI files. That's probably the easiest way to go in and represent the results of a drop test study. Have a couple other studies here. This is our free fall. Because I chose to save it up to a certain point, I'm going to see at least some time steps, right? So it looks like I'm probably only going to see up to 13 time steps because it was about halfway done. I should still be able to see some results though. As we come in here, you can notice that we're pretty close to that maximum level of stress, which makes sense. You're not going to see higher stresses typically much long after that stress has propagated through the actual part. So closer to the point of impact is when you're typically going to see higher stresses. Although it will ramp up as the internal molecules within this particular material are responding to that particular stress. So that's the drop test, kind of in a nutshell here. Let's jump up to impact a little bit. Because with impact, we're actually going to set up a fixture that is going to move itself. Okay, so in this case, we've got a rim, right? We've got a wheel, and what we want to do is we want to analyze the impact of something hitting it, right? Actually, this is amazingly timely. It's a little painful to go through this example. My car has aluminum wheels. I hit something in the middle of I-95 a few weeks ago. That wheel was bent and unusable at that point, right? So this is kind of a painful example that we're going to walk through. But impact is really two different steps. One is going in and setting up a displacement or velocity for one of our pieces. The other part of this is that you really need to fix some of the geometry. Like in this case, I'm actually fixing the center of the wheel, and I'm fixing the bottom base that this thing is sitting on. And the two are in contact, so fixing this is going to propagate there, and it's going to provide some stability for my model as well. So you're really looking at creating a rig of sorts, where you think of this almost like a crash test, where you're actually having an object impact another object, and then taking into account the any type of structural defects. All right, so let's go ahead. These are actually the results from our standard impact test. All right, so we had that block lower into our wheel, and we had it go down 9 inches. And these are the stresses that results. Now these are in English units, not in metric, but 62 KSI, significant stress inside of this particular wheel. Just to go through how to set that up, because you may never have gone through that where you actually set a displacement up. Let's open up our model here, and I'll briefly walk through how we set that up. This is a fixture. Okay, now most of the fixtures that we go through and create, most of the fixtures are hinges or fixed geometry, or they're sliding in one way or another. Here in this case, our fixture is actually going to act as if it's almost an input, an external load. So if we right-click and go to Edit Definition, just to show you all, I set up a fixture that's called On Flat Face, and of course that's going to be relevant when you pick a flat face. If your fixture was relevant to a cylindrical face, then you would pick cylindrical. Same for spherical. There's two ways you can define this basically. One is by translation. The other could potentially be rotation if you are defining this cylindrically or by a spherical face. But the idea here is anytime this button is depressed, it's basically saying that value is being considered. So what this means is that this block is going to move in direction 1 and 2, which in this case are along the X and Z axis, by 0 inches. Now in the Y direction, it's actually going to move 9 inches. Okay, and that's going to put it in contact with our wheel here. Okay, so once we have that stipulated, when we run this particular study, we're going to end up with the stress results that you see right here. Okay, so that's where that 62 KSI come from. Now, one of the great parts, because you're using a nonlinear study, which comes into the simulation premium, you can actually incorporate damping. Okay, so with damping, which damping obviously means that you're going to get some of the lessening of those particular stresses and of the impact each subsequent time. Instead of this thing just continually pressing, it's going to come in contact and dampen and so forth. In that particular case, when we take damping into account, we're actually going to see about 34 KSI. So about half of the internal stress in this wheel due to incorporating damping. I can show you a couple animations where we go through. Let me pull those up for you real quick. I thought I had them in the PowerPoint here, but if we go in and let's just play this particular video, and this is basically an animation of that impact analysis, and we've cycled it through a couple times here. But what you're basically noticing is that top block, which had the displacement fixture attached to it, is coming in contact with our wheel, and then at the finished time slot, you're actually noticing the stress is fully propagated through the wheel. All right, let's talk a little bit about where you go from here. I hope this has been helpful. We will record this, we'll put it up on our YouTube channel, but if you have any questions, I would also mention that at Trimec we've got some great resources for you guys as well.